So in the previous video, we talked about what it really meant for something to be either acidic or basic. When something is acidic, it means it's got more H3O plus or a higher concentration of hydronium ion than it does hydroxide ion. And if it's basic, it's got the opposite. It's got a higher concentration of hydroxide than hydronium. All right. But if you were to try to explain to somebody, how basic or acidic something is, using the seesaw or just saying, it's got a little bit more versus a lot more would not be a very convenient way to express how acidic it is. All right. Generally, when we want to express how much something is, we want some numeric scale that we can use. And in chemistry, what we end up using is the pH scale. And I think you guys should be familiar with pH. So first of all, why don't we just report acidity as just giving the amounts of the molar concentrations of H3O plus and OH minus? First reason is that it would be redundant, all right, because there's a seesaw nature between these, and so if one of these is high, the other one's got to be low, and vice versa, all right. So simply reporting one of them would communicate the relative amount of the other, all right. In a similar, as an analogy, if we wanted to talk about the relative percentage of men versus women, we wouldn't have to report both, because if we reported just on one, that would also communicate the amount of the other. So the other reason that it's that reporting the molar concentrations would be impractical is because of the enormous range of the numbers. All right. One thing about numbers that we probably take for granted is that in most things that we talk about, the difference between large and small is, even though we might think that the difference is big, the numbers aren't that big in terms of how you write them. All right. So, for example, if we wanted to think of the smallest salary in the world versus the highest salary in the world. All right. So, for example, if I were to talk like an average teacher salary would be 5 digits. All right. Let's pretend that it's in the 60,000s. All right. And you compare that to the highest salary in the world. All right. Someone like Bill Gates. All right. Probably makes maybe 10 billion. Let's say that he makes 10 billion a year. And those seem like a huge difference in the numbers. All right. But write both of those numbers down and ask yourself how many times you have to move the decimal to get from one number to the other. All right. In reality, those numbers aren't there. There isn't a huge difference. All right. When we're talking about the difference in how high the H3O plus can be, all right, it goes from anywhere from 10 to the minus 1, all right, which is 0.1, to 10 to the minus 14th, which is this number right here. All right. You would have to move the decimal 13 times to go from one of these numbers to the other. So by comparison, the difference between high and large here is way, way, way bigger than, say, like the difference between the highest salary in the world and the lowest salary in the world, or the highest weight human in the world versus the lowest weight human in the world. All right. This is, in neither of those cases would you have to move the decimal 13 times to get from one to the other. All right. So it's very inconvenient to deal with numbers that that are this different from each other. All right. For example, if I were to show you this number right here and say, well, how many zeros are between the decimal and the number, it's pretty easy to tell. But if I were to say here, well, it would be very easy to just leave out one of these zeros. All right. So for that reason, we end up using a logarithmic scale to express the number. All right. So just in a very simplified form, if the H3O plus concentration is 0.1, which is the same thing as 10 to the negative 1, the pH would be 1. All right. If it's this, which is 10 to the minus 7th, the pH would be 7, and same with so on for pH of 14. All right. One thing that you'll notice that what the pH is very closely, what's most related to, is either the opposite or the negative of the negative exponent if it's reported in scientific notation, But if it's reported as a decimal, it's essentially related to how many times you would have to move the decimal point to get it from where it starts to after that first digit in the number. So for example, here I have to move it one time to get it to be 1. All right, I would have to move it 1, 2, 3, 4, 5, 6, 7 times to move it from here to here. That's why it's pH7. But you can see if it's expressed in scientific notation, it's just the negative of that number right there. All right, so essentially, if you had this as your concentration of H3O plus, that means these would be the molarities of that. This would be an extremely acidic solution, all right, and that would correspond to a pH of 1. And hopefully you remember that low pHs tend to be acidic, all right. If you had neutral water, pure neutral water, this would be the molarities of the H3O plus, not exactly, but very close to that. And that corresponds to a pH of 7, and so on for a basic solution. All right. So the benefit of using the pH scale is that we can now report how basic or something, acidic or basic something is by using a number between 1 and 14 rather than 0.1 to. I'm not even going to say this, but there's a tremendous number of zeros in that. All right. But the one there is one thing that takes a little getting used to is that when you're talking about a high H3O plus concentration, so take a look at these numbers right here. Which number is higher? All right. Okay. This is the larger number. 0.1 is much larger than this number right here. So this is a high amount of H3O plus. But look what it means in terms of its pH. That would give a low pH, all right, and that's because if we compare these high and low numbers in scientific notation, the larger number is the one with the relatively low negative number, whereas the smaller number is the thing with the high negative number. All right, so therefore, when you take that negative of a high number, you end up getting a large number. All right, so it just takes a little bit of getting used to. Like high hydronium ion concentrations give it low pHs. All right. So mathematically, how do we go between these? The equation, and this is available in your data booklet, is pH equals the negative log of the H3O plus concentration. All right. Sometimes this is also expressed in this form right here. Remember, H plus, aqueous H plus, and H3O plus are essentially the exact same thing. There's also a similar measurement of called the POH. All right, and the POH is the negative logarithm of the OH minus. All right, so just a little bit of math. Anytime you put a lowercase p in front of it, mathematically what that means is to take the negative log of that. You can see that in both of these equations. Something that we'll be talking about later is what's called pKa, which is the negative log of the Ka. But it follows the same format. And when do we use this? We use this whenever you have numbers that have a humongous range between high and low. All right. It allows you to basically give the number in terms of how many decimal points are involved rather than what the actual value is. All right. And that those numbers are just easier to deal with. One thing I would venture to guess is that you've heard a lot more about pH in your life than you have POH, all right? And the thing is, if you go back and look at what acidity represents, it represents a relationship between these two values here, all right? So the thing about it is there's no intrinsic reason that we had to measure pH based on the amount of H3O plus. We could just as easily measure pH in terms of expressing this right here. It's just that people like things being in a standardized format, all right? And if I want to know how acidic something is, I want to hear pH because my mind is very trained in what it means. But if something is 1, I understand that means acidic. If it's 14, I know it's really basic, and that's why we tend to just focus on using one of these. And so people just decided to use pH instead of POH. All right, so. Mathematically, pH and POH are related by this right here. pH plus the POH is going to be equal to 14, which is something that you could prove mathematically from this expression right here. All right, so it's just a mathematic manipulation of this expression.